We talked about making a solution, so now we're going to talk about how do you become saturated, that kind of stuff, and also what does it mean to be soluble. So obviously we know that once you start forming an actual thing here, let me actually switch this to action so that I'm writing. Okay, that's fine. So what you want to do is once we actually do this, it doesn't like me right now. Let's see if this works. Now it does. As your solution forms, the concentration is going to increase of your solute because it's breaking down. If you get enough, though, in there, what you can actually have is you can actually go backwards. And so instead of having the solid becoming aqueous, you can actually have it becoming a crystal again. So you can actually have crystallization forming. So you do actually have an equilibrium established. And if you remember, this was actually kind of what our KSP mem was talking about, like, does it dissolve, does it not dissolve? So typically what you want to have happen is you want dissolving, but sometimes you want crystallization. So that's what you're looking at. And again, it's called a dynamic equilibrium. And when you get to this point where you really can't dissolve anymore, and if anything else happens, some of it has to crystallize out, you're called saturated. So when you're a saturated solution, it's way down here. Basically, you have as much dissolved as you possibly can, and if you dissolve any more, some of it's going to have to precipitate out. So each solution has its own saturation point, and you can just look those up and check them and see what they are. But you just need to know. Technically, anytime you're making a solution, you are doing equilibrium. I know you're very excited for it, and we just have to deal with that. So when we say that we're saturated, we're just saying that we have the most solute dissolved that we can. So basically, like if I'm making a solution of salt water, there's a point where I can't dissolve any more salt. It's saturated. If you're unsaturated, we just know that you could actually dissolve more. We know that we could actually do that. We could have more breakdown than we've put in. Supersaturation, we kind of talked about before, and I think I actually showed you a video before of this, but supersaturation is a special situation. It's unstable, and basically you kind of trick the solution into having more dissolved than it should. So what happens is you typically make a supersaturated solution when you're making rock candy, and what you do is you heat up water and you dump tons of sugar in and dissolve it. And then what you do is you let the solution start cooling down, and what happens is it kind of like doesn't know how to crystallize because it doesn't have anything to base off of. And so what you get is a special situation where you're supersaturated. There's a video that I'll show you then of supersaturation. That just kind of shows you, I think we saw before, they talk about little puff ball, that kind of thing, where they show you what it looks like. So what you'll notice is in this one they have to like seed the crystal. So this is supersaturated and then they let it go and then it actually crystallizes.
Oh my god. No, it looks like a little puff ball. Wait, you gotta turn it upside down as soon as it's frozen.
At this time, will all students in Mr. Farmer's homeroom please report to the library? And all students in Mrs. Wiscount's room, homeroom, please report to the Mac lab. Thank you.
All right, so there's a couple things that actually can affect your solubility. So the first thing we said before to actually make a solution is that you need really good solute-solvent interactions. So the better these are, the better the solubility is going to be. The generic term is that like dissolves like. However, you wouldn't want to like use that on an AP test or anything because this is just a very like, it's not really explaining anything. So the rule is if you're polar, you dissolve in polar things. If you're nonpolar, you're dissolving nonpolar things. However, what's really happening is you're referring to the intermolecular forces. So you need to discuss that. Oh, these both have polarity, so their dipole forces are attracted to each other. You want to avoid just saying, oh, it's like dissolves like, because you're not being very thorough. Pressure doesn't really affect liquids or solids because you're not really changing something that's going to affect them. Pressure does actually affect gases. So down here, the more pressure you have, the more soluble gases are. Because if gases are put under pressure, they're going to try and relieve it. And what they do is they actually become more soluble in liquids to try and deal with that. This is just showing you right there that A is regular atmospheric. And you can see there's some solubility here. There are little purple dots. They're showing us some things are soluble. If we look down at the bottom here, B, the pressure is increased and there's more purple dots dissolved. So a couple of questions here. The first one is, why can certain fish only live in very warm water? And the answer to that is that they need a lot of oxygen. They need a lot of dissolved oxygen. If you have a certain temperature, then warm water allows more dissolved oxygen than cold water. And then down here at the bottom here, it says, when you open the lid on a soda bottle, why do you hear the fizzing sound? And the reason that is because a soda can is actually pressurized. So when you open it, what actually happens is the pressure decreases, and the gas bubbles become less soluble, and they actually fizz, which is where you get your carbonation because they're escaping from the liquid. That's why if you have like a 2-liter and you let it sit for a long time, they all escape. They all leave because they're not pressurized anymore. You can see here, we said that typically when you have a certain amount of, when you increase the temperature of water, you actually get more solids dissolved. And I'm sorry, I actually don't hear it. I spoke incorrectly. When you have the warm water, the gases actually are less soluble. So I actually lied to you about the fish. The fish thing is when they need a certain amount of oxygen, and if they have too much, it can make them sick, and so actually they need a specific amount. If you heat up soda, what's happening is that you're making the CO2 molecules less soluble, so they're going to escape. And a big thing that you don't really think about is thermal pollution. So thermal pollution is basically when you make water too warm. And what that does is it decreases the amount of oxygen, and that affects our aquatic life. So certain fish can't live without a certain amount of oxygen, and they can't survive. Aquatic plants need a certain amount, and it can actually, you don't really think about it, but you can change in a whole ecosystem or destroy an ecosystem by thermal pollution. The next few slides are just graphs. This first graph, you can just see that as our temperature increases, solubility does increase. There's one exception here, and that's this guy right here. He's the only one that goes down, but for the vast majority, they all go up. And if you're reading this graph, they would just say, hey, at 30 degrees, how much of something can be soluble, or which one's most soluble, that kind of stuff. So if we're looking at this one, the guy that would be most soluble, it would either be, depending on the temperature, would either be sodium nitrate or calcium chloride. And the guy would be least soluble, depending on the temperature, would probably be the cerium sulfate, but you'd have to look at the temperature situation. This graph is just showing you solubility of gases with temperature, and you can see that they decrease. So the higher your temperature, the less gases are going to be dissolved in things.